Hey, Manasvi, so I noticed that you're opening the PDF in the browser. Maybe
Yeah,
Acrobat Reader would be a
yeah, I tried opening. So let me give it a shot once more. If it,
okay. Cool,
yeah.
cool. Let me know if you want to call for technical help. I think we can also do that.
Okay. So I think only 2 minutes are remaining as of now.
Sure. Uh, should I call for technical help?
Sure.
Okay.
Sure. Umang, uh, so this seems to be working fine.
You just make
Yeah,
it
yeah.
full screen. Control L should do it.
Sure.
Yeah, that looks good. Okay,
Okay.
so let's get.
Sure. Please let me know 1 minute before my time ends.
Yeah, I'll do that. I'll do that.
Thanks a lot.
Okay. All right, everybody. Welcome back to Approx for the third day. This is the first session. Just a reminder that so in this session we will have four talks, and then after that there will be time for discussion outside as well, and that will be followed by the keynote talk by Vera Traub. So I hope you'll be able to join for that as well. Okay, so the first talk today is going to be by Manasvi Parashar, and he will talk about the query complexity of global mincut. Go ahead, Manasvi, please.
Thanks a lot, Umang. Hi everyone, I'm Manasvi. The title of the talk is Query Complexity of Global Minimum Cut. This is a joint work with Arijit Bishnu, Arijit Ghosh, and Gopinath Mishra. All of us are from Indian Statistical Institute, Kolkata. So let us start by recalling the global minimum cut problem. So let G be a simple graph with n vertices and m edges. A cut of G is simply a partition of the vertex set into S, a subset of the vertices and its complement. The size of this cut is the number of edges with one endpoint in S and other endpoint in its complement. And the global minimum cut of G, which we are going to denote by this notation, is the size of the smallest cut of G. So let us take a couple of very simple examples. So here G1 and G2 are two graphs on 8 vertices each. And this is the global minimum cut, and the size of minimum cut is 1 and 0 respectively. G2 is disconnected in particular. So how about finding global minimum cut in this huge graph, which might have come from a social network where nodes represent people and edges represent friendship connections between them. Uh, the famous algorithm by Karger and Steen will find us a global minimum cut in time O tilde n square. So, however, this time is too large for a graph this large. O tilde n square is huge. So, in this talk, what we are interested in is finding global minimum cut or an approximation to it in sublinear, in cost that is sublinear in the input size. A word on the notation. So I'm going to use O tilde to hide polylogarithmic multiplicative factors. Okay, so now let us define the problem of interest. So the minimum cut estimation problem, in this problem, an algorithm is given input a parameter epsilon and access to an unknown graph G. And the goal of the algorithm is to output 1 plus minus epsilon approximation to the minimum cut of the graph. So what does access mean? Unlike usual setting of algorithm design, we have restricted access to the graph. We assume that there is an oracle that stores the local properties of the graph. So, for example, in the huge graph that we saw, the nodes, which are people, store information about their friends. And then there's a fixed set of questions that we can ask this oracle about the local properties of the graphs. These questions are called queries. So I'll explain this formally in the next slide. And the goal of the algorithm is to solve the minimum cut estimation problem by making a sublinear number of queries. So by making number of queries which is much smaller than the input size. So this will become clear once we look at our results. So but the first thing that we need to define is the query model. So this is the one of the main slides of this talk. And in this work, we study the local query model. So this is one of the most well-studied graph query models. And the local query model allows three types of queries: a degree query, neighbor query, and adjacency query. With a degree query, an algorithm can query a vertex U, and the oracle will return the degree of that vertex. With a neighbor query, the algorithm can query for a vertex U and an index I in 1 to n, and the oracle will return the ith neighbor of that vertex if it exists, or will just give a special symbol if it does not. And with the adjacency query, the algorithm can query a pair of vertices, and the oracle will return 1 if there is an edge between them, and it will return 0 otherwise. So in our upper bounds, that result that we will see, we are not going to use adjacency queries. However, since our algorithms are all randomized, we are also going to assume that our algorithms have access to free random coin tosses. So in summary, the algorithms that we are going to look at are going to use degree query, neighbor query, and free random coin tosses. So before going to our results, let us look at the history of minimum cut estimation problem in the area of sublinear algorithms. So to the best of our knowledge, we did not know of any local query based algorithm for this problem, for the minimum cut estimation problem. However, in 2018, Eden Rosenbaum, they showed a lower bound of m by the minimum cut of G in order to solve this problem in the local query model. In slightly stronger query model called the global query model, this problem has indeed been studied. Rubenstein et al. In 2018 studied this model in the cut query model. With the cut query, an oracle now takes an input, a subset of vertices, and it returns the size of this cut. That is the number of vertices going from S to its complement. And so this query is global in nature. And Rubenstein et al. Gave a O tilde and upper bound for finding minimum cut in the cut query model. And a lower bound of n by log n follows from a result of Babayan et al. From 1988. So in the cut query model, this problem is completely understood up to logarithmic factors, of course. So now let us go to our results. So we show that the minimum cut estimation problem can be solved with high probability using an expected number of minimum of m plus n, m by min cut of G many degree and neighbor queries, along with some polylogarithmic factors. So observe that from the result of Eden and Rosenbaum that we saw in the last slide, our upper bound result gives the tight query complexity of estimating minimum cut in the local query model. And this is the main takeaway that I want you all to have from this talk, is that with this result, we now have the tight query complexity of minimum cut estimation in the local query model. We also give two lower bound results. The first one is for finding the global minimum cut, and the second one for finding the exact size of global minimum cut. So both these lower bounds are omega n, and kindly look at the paper for the formal statement of these theorems. However, two remarks are in order. The first one is that these lower bound theorems are the techniques that we used are similar to that of Eden and Rosenbaum from 2018. And also these lower bounds hold when the algorithm is not only given access to the local query, but is also given access to random edge query. So with this additional power also, these of the above lower bounds are going to hold. By random edge query, I mean each query of the algorithm will now return it an edge uniformly at random, edge of the graph uniformly at random. Well, so these are our results, and let me just give a very high level proof of our upper bound theorem. So in our upper bound theorem, the first thing that we show is a structural lemma. So our structural lemma is that, okay, so let us assume that we know a lower bound, t hat, on the size of minimum cut of the graph. If we know such a lower bound, then our structural lemma gives a sampling procedure. that will generate a random subgraph H of the unknown graph G, such that all cuts of G are going to be preserved in H with high probability. So in particular, the min cut is also going to be preserved in H with high probability. So using the structural lemma, we can already come up with a algorithm to solve the minimum cut estimation problem. Yeah, but of course, this lemma assumes a lower bound on the size of the minimum cut. And our main technical lemma gives us a algorithm that will find a lower bound on the minimum cut of G with high probability. So using these two lemmas, we can prove our upper bound result. And please have a look at the full version of the 20-minute version of this talk, where we give almost complete proof of this upper bound theorem. And yeah, and so this is the main takeaway from flashing it again. That the main thing that we show is that is tight query complexity of minimum cut estimation in the local query model. So thanks a lot. See you in the discussion session. Thank you.
Okay, thanks, Manas.
Thank you.
So I completely forgot to mention that you can come up to a mic and ask questions, or you can put them in chat, and chat is probably the better way.
Oh, so
I don't.
I mean,
No,
sorry, I
that's
was
okay.
only looking at my screen at this point.
That's fine. So I'll tell you the question. So Karthik
Yeah.
asks, is there a reasonable local query model for the weighted case?
Yeah, I mean, for the weighted case, in fact, so yeah, so we need to access the weight somehow. So these local query models are motivated by the adjacency matrix and adjacency list data structures. So one might think of adjacency matrix data structure where the entries have weights, and one can query the entries of the matrix asking for weights. So for example, instead of adjacency query, one might the oracle might return the weight of the edges and not just whether there is an edge or not. So that might be one. Yeah.
Dishant asks, I don't understand the question. So what is the lower bound when cut size is 0?
Yeah. So in when the cut size is 0, then lower bound is m plus n. So Eden Rosenbaum's lower bound when cut size is 0 is m plus n. So yeah.
Good. I think yeah. Let's
Yeah. Thanks a lot for the
let's
great
keep moving.
questions. Thank you.
Okay. Thanks, Manasvi. Okay. So I'm going to ask. I think John is the next speaker. John, could you come up and set up? Yeah.
All right. Right. You see it? I cannot see or hear anyone, so it's unclear to me whether you can currently. I can now, yes.
Yes. Humang, can you hear us? Because I don't hear you. John, do you hear Humang?
No.
Okay. Is it just us, or is anyone not able to hear Humang? Can you please write on the chat? Okay. Yeah, okay, good. It seems there are some problems. Okay, that maybe we try to fix, but okay, meanwhile, we can continue. So, John, you can go ahead with the presentation if you want. Yeah?
Okay. Okay, thank you. Thank you.
welcome.
Yeah, hello everyone. Welcome to the abbreviated version of an optimal algorithm for triangle counting in the stream. So this is joint work with Rajesh Jayaram. So I want to start by just talking briefly about what I mean by in the stream. So streaming graph algorithms are a class of algorithms for very large graphs that arrive one edge at a time. So by very large, I mean, think, much too large to fit in memory. And by one edge at a time, I mean that you see the graph as just a list of its edges presented in some adversarially chosen order. And so examples of cases where you might care about this are things like, say that you see some really large social networking graph as a series of events of the form where Alice became friends with Bob, Bob became friends with Charlie, Charlie became friends with Darlene, etc. And you want to calculate some property of this graph while not storing all of these many, billions of friendship events. Or for another situation, suppose that you have some really large graph stored as a file on disk. So making random queries to it is prohibitively expensive. But what you can do is read this whole thing off disk and stream it and maybe store some small amount of information in main memory. And you want to estimate properties of this graph this way. Now, the problem that we're going to consider in this talk is the problem of triangle counting. So this is, you see this stream of edges, and what you want to know is how many three-cliques, how many triangles are there in the full graph. And the problem of counting triangles has been studied in practical context because it's related to, for instance, this concept of the transitivity coefficient in social networks. It's been used for things like spam detection, but it's also of particular theoretical interest because it is, in some sense, the simplest graph counting problem that requires non-local information. By non-local information, what I mean is, say you wanted to try an even simpler graph counting problem, like counting the number of length 3 paths in the graph. Well, that you can find the number of these paths that are centered at a given vertex just by looking at what its neighbors are. Whereas if you want to count the number of triangles, you have to join together information about the neighborhoods of at least 2 different vertices. So now, this the bad news about this problem is that thanks to this result of Braverman, Atrovsky, and Vilenchek, we know that unless you assume that the number of triangles in the graph is really large, it's actually impossible in general to get sublinear upper bounds on the amount of space that you use. So what they showed is that there's this family of graphs such that if they have m edges, and even if you guarantee that they either have theta m triangles or 0 triangles, distinguishing between the 2 cases still requires storing essentially the entire graph. But the good news is that the family of graphs you use to prove this is a pathological family of graphs. It has this really specific structure that every single triangle in the graph has to share just one edge. And so intuitively, the reason it's hard to distinguish between these 2 cases is because there's this one critical edge that you have to find. So a natural question to ask is, can we do better if we cap the number of triangles that are allowed to share a single edge? So if you say, okay, we're going to introduce this new parameter, delta E, that maxes the number, that's the maximum of the number of triangles that can share an edge, this lower bound suddenly becomes omega of delta E. And this is for the just distinguishing 0 and theta m triangles case. And for the remainder of the talk, I'm just going to consider this case. If you want to know how this generalizes to other numbers of triangles, see the full version of the talk. Now, a fair amount of work has been done in this with this additional parameter. There's this algorithm of Pei and Sirakakis that gives you delta E plus square root m space. And we have this lower bound that says that this is actually optimal. You can get a separate lower bound even in graphs where only one triangle can ever share an edge, such that you need omega m space to kind of solve this situation. But this lower bound is another one of these pathological graph families. This time where you require that every single triangle shares a vertex, and like in the case I mentioned before, this lower bound when you restrict the number of triangles that share a vertex to delta v, this lower bound now becomes square root delta v. And so with this extra parameter, I just want to give you like a quick view of like what the previous work is here. So now you have this algorithm of Pei and Tsourakakis, which is tight when you allow delta v, the maximum number of triangles sharing a vertex, to be as large as you want. We have this other algorithm that's like kind of like tight to the lower bounds, except for having an additive n to the 1/3 term. And then there's this other line of work which parameterizes the problem by the maximum number, by the max degree of the graph, d, and so it gets like a d space, and which is non-comparable to these other two. And so the algorithm I'm going to tell you about here is one that achieves delta e plus square root delta v space. That is, it's tight to these lower bounds up to log factors, which I've been ignoring so far in the talk and will continue to ignore for the rest of it. And it also subsumes this like other line of work based on the max degree, because you can bound both delta e and delta v in terms of d. So now I'm just going to finish off by just briefly telling you what the algorithm is. So the idea of our algorithm is that you combine what we call edge sampling and vertex sampling. So the way it works is, and I want you to recall that the model we're thinking of is you're seeing the graph as just like a stream of edges, one edge at a time. So you sample vertices with probability p. Again, since you're seeing edges, you shouldn't think of this as storing vertices so much as you have a hash function that tells you for each vertex, is it sampled or not? And then whenever you see an edge incident to one of your sampled vertices, you keep it with probability q. And then finally, whenever you see an edge, you look at the edges that you've kept so far and say, does this edge complete a triangle with some pair of edges in my existing store? And if it does, you increase your count of triangles by 1. So this means that for any triangle, your probability of counting it is exactly pq squared. If you because what you have to do is you have to sample the vertex that connects its the first two of its edges to arrive, and then keep both of those two edges. So your estimator is eventually just going to be this the number of triangles you've counted divided by pq squared. So how do you choose these parameters? Well, for each of your edges, you're keeping it with probability pq. And for each triangle, you're going to count it with probability pq squared. So that tells you that you probably want p to be like as small as possible, because while q is comparatively large, because that gets you the largest number of triangles for your like space budget. But the problem is, and this is where this like lower bound in terms of delta v comes in, the smaller p is, the more it matters whether or not you sample any given vertex that has many triangles associated with it. And so the larger delta v is, the larger you have to set p to be, so the less efficiently you use your space budget. And like setting p and q appropriately, therefore gives you this like delta e plus square root delta v sample count that you require. And so that's all I had to say about that. So I'd like to just close out by putting up the fully parameterized results on the slide, and then ask if there are any questions.
Okay, yeah, thanks, Sean. Sadly, I'm going to just, in the interest of time, like, I think I disappeared again. John, can you hear me?
Yes. Okay, now I can't hear you.
Yeah, no, I was saying in the time.
So sorry, I haven't been able to hear anything.
Let's keep the questions.
Can you hear me?
Discussion period, for the discussion session.
Okay. Thank you.
Sorry, am I audible now?
Yeah. You're saying you want to hold questions to the discussion period. Okay.
Okay. Now, would you like to? Yes. Sorry, apologies for my connection. Noah, do you want to set up? I think Noah is the next speaker.
Hello, can you hear me?
Yes, yes, we can hear you. You want to share your screen? Okay, great. So the next talk is going to be by Noah, and he's going to talk about every ordering CSP is approximation resistant in the streaming setting. Go ahead, Noah.
Right, thanks. My name's Noah, and I'm going to be telling you about our work called Every Ordering CSP is Approximation Resistant in the Streaming Setting. And this is joint work with my two collaborators, Madhusudan and Santoshini Velusamy. So first, I'm going to tell you sort of what an ordering CSP is. And I'm going to start by telling you the simplest example of a problem that fits. Sorry, I'm hearing a lot of noises. But in the simplest problem that fits this ordering CSP framework is called the max acyclic subgraph problem. So in this problem, an instance, which we'll denote by psi, is a directed graph on the first n natural numbers. And the goal of an algorithm for this problem is to calculate the value of an instance. And by value, we mean the largest fraction of edges which point forwards with respect to any possible way to order the vertices of the graph. So for instance, here's a graph, and its vertices are ordered in some way, and this is not a particularly good ordering because there are 9 edges and 4 of them point backwards. But if we permute the vertices of this graph into a different order, we can actually make all the edges point forwards. So this ordering witnesses the fact that this instance of the MAS problem has value 1. So in this talk, we're going to think of this max acyclic subgraph satisfaction problem or ordering CSP. So instead of thinking of an edge, we'll think of a constraint. And instead of thinking about an edge going forward in a particular ordering sigma, we'll think about the corresponding constraint being satisfied by that ordering. So in particular, vertex u to vertex v will be satisfied by an ordering sigma if sigma places u before v in the ordering. And now the MAS value of an instance is just over any possible ordering of the vertices, or you can think of variables in the instance, what the highest possible fraction of constraints that can be satisfied is. So this MAS problem to a whole class of problems, which are called maximum ordering constraint satisfaction problems. So in all of these problems, the solution space of possible assignments is still the set of all permutations on, say, the first n natural numbers. But now we have k-ary constraints, and they say something about the order of k positions in an assignment sigma. So just some notation, given J, which is a k tuple of indices, and an assignment sigma, we can define sigma restricted to J as just the value sigma of J1 up to sigma of Jk. So a max OCSP problem will be specified by a constraint function pi, which specifies some allowed orderings on k variables. And in the max OCSP pi problem, a constraint J says that the order of an assignment sigma restricted to J must satisfy the property pi. So this is a lot. For instance, for the MAS example, we have k equals 2 because each constraint constrains the order of 2 positions in an assignment sigma. And the constraint function is the function from S2 to 0, 1, which is supported on the ordering 1, 2. And another example of a problem which fits this framework is called the maximum betweenness problem. In this problem, it's k equals 3. So each constraint says something about the position of 3 variables in an assignment sigma. And the constraint function, pi, will be supported on the orderings 1, 2, 3, 3, 2, 1. So in other words, an assignment sigma will satisfy a constraint UVW if and only if sigma of V is in between sigma of W and sigma of U. And apparently this problem has some information in bioinformatics that I personally don't know very much about. Okay, so how approximable are these maximum OCSP problems? So in this talk, we'll say that an algorithm A is an alpha approximation to the max OCSP pi problem if for every instance psi, A of psi outputs a value which is between the value of psi and alpha times the value of psi. So our approximation factors alpha will be real numbers in between 0 and 1. Which is addressed in this talk is how good of an approximation can we get problem with an efficient algorithm. So something that's important to note is that the max CSP pi problem has a trivial approximation. Is what we call rho of pi, where rho is just the probability that a random ordering will satisfy any particular constraint. So the question is, can we beat this sort of trivial rho factor by some constant amount? So just, to restate, can the max OCSP pi constraint function pi be rho plus epsilon approximated by an efficient algorithm for some constant epsilon? And this question of the approximation resistance of max OCSPs is sort of what we address in this talk. So what's known about the approximability in the classical setting? There are some results which show that it's NP hard to get good approximations to these maximum betweenness and maximum acyclic subgraph problems, although they're not optimal. So like, for instance, we know that you can't get a better than half approximation sort of based on NP hardness assumptions to maximum betweenness, but the optimal would be ruling out better than rho equals 1/3 approximation. We do know that for every constraint function pi, you can't beat the trivial approximation in polynomial time, assuming the unique games conjecture. And this is due to a seminal result of Guruswamy, Hostad, Manokaran, Raghavendra, and Charakar. But without the unique games conjecture assumption, we don't know how to get anything optimal just based on NP hardness. So in this work, we consider the approximability of so in the streaming model, an algorithm will only get polylogarithmic space in the number of variables in an instance of the ordering CSP, and it only gets one pass through the list of constraints in a particular instance of the max OCSP problem. And the reason why this sort of model makes sense to study is that there's been a recent line of work which has proven for various CSP-like problems, unconditional approximability or inapproximability results, typically via reductions to communication games. So the question is, in this streaming model, this limited model of polynomial time-esque algorithms, what can we get in terms of inapproximability for ordering CSPs? So what was known previously before this work? So at least to the best of our knowledge, there were no inapproximability results that were known for any max OCSP problem aside from the max acyclic subgraph problem, first problem that I talked about at the beginning. And for the max acyclic subgraph problem, there was a work actually which was in Approx 4 years ago, which ruled out better than 7/8 approximations in sub square root n space. And this was via some gadget reduction argument from the Boolean hidden matching problem. And this 7/8 was improved to a 3/4 via a streaming reduction from the unique games problem. But this 3/4 is still short of, what we would really like to show is that you can't even get a half plus epsilon approximation. And that's exactly what we do in this work. So in this work, we show that for every constraint function pi, the max OCSP pi problem can't be streaming approximated constant factor even in sublinear space in the number of variables in an instance. So no sublinear space streaming algorithm can distinguish instances of the max OCSP problem that have very high value, say at least 1 minus epsilon, from very low, sort of close to trivial value, like at most rho plus epsilon. And note that, like, compared to the results on the previous slide, this is an improvement both in terms of the space bound. And in fact, the space bound is basically optimal due to, at least in the way that we define our model, because in the way that we define the model and is sort of standard in the streaming literature, there's no restrictions on the time an algorithm can use, only on the space that it can use. So once you have unlimited time and linear space, what you can do is, given your instance psi, you sample a linearly large subinstance, say psi tilde, and then say in exponential time, exactly calculate its max OCSP value. And then since psi tilde is so large, you can use concentration bounds to show that its value is close to the value of the entire instance psi with high probability. And finally, I'm just going to say a little bit about the ingredients that are used in our proof. So firstly, we use streaming and approximability results for so-called non-ordering CSPs, which are very recent and due to Cho, Golovnev, Sudin, Belusamy, and Velinker. So by non-ordering CSP, I mean a constraint satisfaction problem where instead of the assignments being orderings in SN, they're assignments of every sort of vertex or variable to a value in a finite alphabet size Q. And in our case, the alphabet size will be a very large constant. And then secondly, we use a notion called coarsening for ordering CSPs. And this is essentially identical to a sort of similar notion that was used in the Guruswamy et al. Work that showed the UGC hardness estimation of OCSPs. And this coarsening is essentially a way to take an ordering CSP and turn it into a CSP over a large but constant alphabet size. And finally, in order to actually make the proof go through, we have to do this analysis of small set expansion properties of graphs, which are drawn from the no distribution of instances produced by this Cho et al. Work. And this distribution is some type of random graph distribution, although it's sort of weird, like there's some subsampling of a union of random matchings. But essentially we drill down into how that's defined and show that it has certain expansion properties required to make the proof work. And yeah, that's the talk. Thank you.
Hi, can you hear me?
Yeah, we can hear you.
Okay,
Please go ahead.
good. Just a second. Good. Can you see my screen?
Yes, we can see your screen.
Great, thanks.
Okay, so the next talk is going to be on fine-grained completeness for optimization in P, and Alejandro will be giving the talk. Please go ahead.
Thank you. Yes, hi everyone. I'm going to talk about our paper Fine-Grained Completeness for Optimization in P. My name is Alejandro Casis, and this is joint work with Carl Brinkman, Nick Fisher, and Marvin Kuhneman. So I want to give you a short summary of what is this paper about. We introduce a new class of polynomial time optimization problems, which includes many natural and interesting problems that have been studied in the literature. We then show that maximum inner product, a particularly interesting problem from this class, turns out to be complete under fine-grained reductions for the entire class. This completeness result applies for both exact and approximate computation and has some interesting consequences. To motivate this line of work, one of the goals of fine-grained complexity is to show tractability and intractability for problems that can be solved in polynomial time. For example, distinguish which problems need quadratic time from those that need linear time, or that can be solved in linear time. There are many nice results in this field where we have conditional lower bounds for some specific problems, but most of these results turn out to be problem-based, in the sense that we know many reductions and we have many conditional lower bounds, but most of these are tailored for specific problems. And we lack, in general, an understanding of larger classes of problems, and in many cases, relation among problems that seem to be very similar to each other. Ideally, we would like to have a better understanding of some large class of problems for which we can prove conditional lower bounds, let's say for every problem in this class, to get a better understanding of the complexity landscape. A notable exception is this beautiful work by Gao, Impagliazzo, Kolokolova, and Williams from a couple of years ago, in which they show the first completeness result for a decision problem in P. In particular, they show that orthogonal vectors turns out to be complete for the class of first-order model checking problems. The details don't matter too much, but the point is that they identified a core problem, a decision problem in P, which is complete for a larger class of problems, which is exactly making progress in this direction of getting a better understanding of a larger class of problems within P. Now, in this paper, and our work can be seen as an analog of Gao, Impagliazzo, Kolokolova, and Williams' result, but now for optimization problems. So I want to start by first telling you what is this class of problems that we define, and then what is our main result. So the class of problems that we consider, we call it Max SP, and it's inspired by the class Max SNP, which was introduced in classical work by Papadimitriou and Yanakakis already 30 years ago. Recall that this class consists of problems which are defined by formulas of the following form, where we maximize over a relational structure and we count the number of tuples of variables y, which satisfies some given formula phi, where here G, you can think of it as the input structure.
So I'm not sure what happened. Alejandro disappeared. I'm hoping he has some minor technical difficulties and will be right back. Let's see, is he online? I don't see him at all. Let's just wait maybe a minute or two. Okay, I'm sorry. I don't really know what happened. I think it's almost time for the discussion section, anyways. Hopefully, we'll be there. If not now, in a minute or two. And of course, presentations. The full presentations are also viewable, so please do that. I think maybe let's just head for the discussion now, and yeah, and hopefully he'll be there. And after that, we'll all have the keynote talk as well. Okay, thanks everybody.